Welcome to The Explainer. Okay, chemistry exam coming up, don't sweat it. We're going to supercharge your revision today with a deep dive into electrolysis. You know, that chemical process that gives us everything from shiny car bumpers to the super pure copper inside our phones. So let's start with stuff you see all the time. Think about that gleaming mirror finish chrome on a classic car, and these ultra pure sheets of copper that are, they're basically the backbone of all our electronics. So how do they get metals so perfect and so pure? Well, the answer is this really powerful industrial process. It's kind of like a chemical superpower that works right down at the atomic level. And today, we're going to break down exactly how it all works.
All right, let's get into it. This superpower is called electrolysis. And it's really all about using electricity to make chemistry happen exactly when and how we want it to.
The easiest way to think about it is like a controlled jolt of electricity that kind of convinces atoms to break their bonds and form new ones. You see, some chemical reactions are just stubborn. They won't happen on their own. They need a little push. And well, electrolysis, that's the push.
To get this to work, you just need a simple toolkit. First up, an electrolyte. Just picture it as a liquid highway for ions to travel on. Then you've got your two electrodes, the anode, that's the positive one, and the cathode, which is negative. And hey, for your exam, a great way to remember what happens where is just to think an-ox and red cat. So the anode is for oxidation, and reduction happens at the cathode. Super helpful, right?
Okay, now here's where it gets really interesting. The final outcome, like what you actually end up making, it changes completely based on one simple choice: what your electrodes are actually made of. Just take a look at these two setups. Over on the left, we've got inert electrodes made of carbon. Think of them as just passive observers. They're just watching the show. But on the right, those copper electrodes are reactive. They are in the game. They're active players. So when you use these inert carbon electrodes, you can actually see what's happening. Oxygen gas starts bubbling up at the anode. At the same time, you get this copper coating on the cathode. And this is a key detail. Because those copper ions are being pulled out of the solution, that classic blue color starts to fade away. But when you swap those out for reactive copper electrodes, the whole story changes. The copper anode itself actually starts to dissolve into the solution. It's constantly replacing the copper ions that are plating onto the other side. And because of that, the concentration of copper ions stays the same, which means the blue color doesn't fade. Not at all. Okay, let's put this all together. You can see it right here in this table. That one choice, inert versus reactive, it changes everything. It changes what happens at the anode, it changes the color of the solution, and most importantly, it changes the entire reason you do this in the first place. This is absolutely a key concept you've got to remember for that exam. All right, so now let's see how this idea of reactive electrodes is used in a massive, real-world application: purifying copper. So here's how they do it. Industries start with a big, dirty block of impure copper. That's the anode. And on the other side, they use a thin starter sheet of really pure copper. That's the cathode. The whole goal is just to move the good copper from the dirty side to the clean side and leave all the junk behind. It's actually a pretty cool atom-by-atom journey. The impure anode dissolves, releasing just the pure copper ions. These ions then travel across that electrolyte highway we talked about, and they deposit themselves onto the pure cathode, building it up layer by perfect layer. And all the impurities, well, they just fall straight to the bottom. And here is the final result. The impure anode on the left is almost gone, while the pure cathode on the right has gotten way bigger. But check out that sludge at the bottom. That's not just waste. It often contains super valuable metals like gold and silver. So get this, in the process of purifying copper, companies can actually recover precious metals, which makes the whole thing incredibly efficient and, profitable. Okay, so let's check out the other main use for these reactive electrodes, giving everyday objects a brand new, shiny, and protective surface. This is called electroplating. It's how we get that tough, rust-proof chrome on car parts, or that beautiful thin layer of silver on nice cutlery. It's all about looks, yeah, but also protection. And the process is basically identical to copper refining, just with a different goal. The object you want to plate, say this nickel spoon, you make that the cathode. The metal you want to coat it with, in this case pure silver, that becomes the anode. You turn on the power, the silver anode dissolves, and the silver ions travel over to give that spoon a perfect, shiny new coat. It's that simple. And here's a cool piece of trivia for you.
Ever see cutlery stamped with EPNS? That stands for electroplated nickel silver. But here's the secret. Nickel silver is just a fancy name for an alloy of copper, nickel, and zinc. It has literally zero actual silver in it. The only silver is that incredibly thin layer that's plated right on top.
Okay, so far we've seen how electrolysis uses electricity to force a chemical change. But what if we wanted to do the reverse? Can we use a chemical reaction to make electricity for us? Oh, absolutely. And that's exactly what things like batteries and fuel cells do. So while electrolysis turns electrical energy into a chemical change, a fuel cell just flips that completely around. It takes a chemical reaction and turns it into useful electrical energy. A hydrogen-oxygen fuel cell is a perfect example of this. It's basically running the electrolysis of water, but in reverse. You combine hydrogen and oxygen gas, it generates clean electricity, and the only thing that comes out the other end is pure water. How cool is that? So what's the big takeaway here? It's that electrolysis is way more than just a topic for your exam. It's kind of the hidden engine behind our modern world, right? It's purifying the metals for our gadgets. It's protecting and beautifying the stuff we use every day. And really, understanding this fundamental link between electricity and chemistry, well, that's the key to unlocking the next generation of energy tech. And this brings us to really the biggest challenge of all. As this quote says, our energy-dependent world is absolutely starving for new, cleaner sources of power. So the big question is, what will the next generation create? Mastering these fundamental processes, everything from electrolysis to fuel cells, that's the key to building a cleaner, more efficient future. Thanks so much for joining this explainer. Now go ace that exam.